Thank you.
So, hi everybody, welcome to another seminar for the Explainable Fuzzy Challenge. We've recently had a couple seminars from guest speakers, and today we have another in Dr. Barnabas Bede. He's going to be giving a talk on gradient descent in fuzzy systems. Dr. Bede is a professor at DigiPen. He earned his PhD in math from Babes Bolyai University in Romania. Hopefully I pronounced that correctly. If not, I'm sure Barnabas can correct me. His research interests include fuzzy sets, fuzzy logic, and image processing. He serves as an editorial board member on the journal Fuzzy Sets and Systems. He joined DigiPen in 2011. Before that, he also held positions in Romania, Hungary, University of Texas at El Paso, and University of Texas Pan American. At DigiPen, he develops class materials for fuzzy sets and various topics in mathematical analysis. He's also heavily involved in the North American Fuzzy Information Processing Society, where he serves on the board and other organizational roles, as well as contributing research. So join me in welcoming Dr. Barnabas Bede to give a great talk on gradient descent in fuzzy systems.
Thank you very much. Thank you, Tim, for the nice introduction, and the pronunciation for Bolyai was correct. For Babe, the other one is Babes, but was,
okay.
was partially correct. So thank you very much for the introduction. No, it's yeah, I would read it the same way in English. So yeah, thanks for the introduction, and yeah, I'm glad to be here and excited about this year's competition. Last year we had a team and they had learned a lot during this during the challenge and the talks and everything. So I'm looking forward to have a new team participating this year as well. And yeah, I hope that you will find the talk interesting. Let me share my screen. So can you see my screen?
Yep, looks good.
Awesome, thank you very much. So I'll be talking about gradient descent in fuzzy. Yes, and well, first we will introduce the general idea behind gradient descent. Then we'll talk a little bit about deep learning. Then we go into fuzzy systems, and you already had several talks about fuzzy systems and of what kind. Yeah, what is different for this talk? I'm going to just remind you what were in the previous talks and go from there. How would we learn in this setting? Then we will talk about ANFIS, Adaptive Network-Based Fuzzy Inference System, that was developed a long time ago, kind of almost at the beginning of the neural network field. Kind of one of the first contributions in that field was yeah, not far from the origins of neural networks. The fuzzy system version of them was already developed, and I will also talk about an application that we developed with a student on El Nino Southern Oscillation. So what we can say about gradient descent? Well, there are two directions within explainable AI. So what is explainable AI? We try to make AI to be not a black box. So typically you would think of an AI application as you have an input, then you have a black box, and then you have an output. And we want to replace, we want to make it explainable. So there are two possible ways to do that. One of them would be to replace the black box technique with interpretable methods. So here you basically cross out the black box and you replace it with a different technique. Yes, say for example, I don't know, fuzzy systems, for instance, or could be something as simple as decision trees that are still in the explainable AI realm. Another thing is to interpret black box techniques as much as possible, extracting knowledge from data as fuzzy rule bases. So fuzzy rule bases can relate the input to the output in a natural way through the if-then rules. And basically, if we develop fuzzy if-then rules, then we can interpret rule bases. So method number one is completely replacing the for example, let's take that black box is typically a neural network currently. So this neural network is completely replaced in the first version. In the second version, we train the network and we try to interpret it as a fuzzy rule base through the ENFIS architecture. So that's the different idea that we will discuss both of them in this talk. First, let's take a look at gradient-based learning. So I'm not sure whether everybody took already Calc2 and everything, vector calc, and I wanna take a moment to remind you about how gradient descent learning works. So this is an image of the gradient of a vector field. Several machine learning algorithms rely on the gradient concept. So for example, these are level curves. So this is a 3D curve, and these are level curves on that. So these level curves basically would be different levels higher on the outside. And I don't know if you can see the little hand. Can you see the little hand that I'm
Yes, we can see it.
manipulating? Okay, so these are like higher level sets. Like let's say this is at level 7. So the z value for this is a 2D graph, and this z value for this is 7, like 6, 4, 5, 4, 3, 2, 1, 0 at the center, let's say. Yes. So gradient basically is a vector field that is perpendicular to these level curves. The gradient is defined as the partial derivatives of the function with respect to the variable. So here we have two variables, x and y. The partial derivative with respect to those is basically giving birth to a vector. So that vector has two components, the two partial derivatives, and that vector points towards the steepest ascent on the surface. So the direction of that would be this blue one, this little blue, I didn't put an arrow, this should be an arrow because it's a vector. This blue one would be the direction of the gradient, but we don't want to, usually we want to minimize error. So let's assume that this is error for some random application that we can imagine. So in this case, we don't want to go to the direction of gradient ascent. We want to minimize the error. Therefore, we go opposite to that direction. Yes. And if we go opposite to that direction, we go along the orange vector, in the direction of the orange vector, a small step. So a small step in this direction will take us on a lower level curve. Then we repeat the process until we reach the center of this. Okay. Yeah, so when I'm clicking, then it's going away. So this orange vector will take me slowly to the minimum error. So this is basically the idea of the gradient descent method. We don't want to make too big steps. So the steps that we take are going to be multiplied by a certain small value called learning rate. We don't want to make too big steps, because imagine that if you take a big step from here, you end up with a for example, right here on this blue one, then you take a bigger step from there. You could explode the algorithm very easily in a couple of steps. Yes. So if the steps are too big, even though we are near the minimum, we could be just catapulted out of this region. Yes. So we take smaller and smaller steps until we reach the minimum value. Yeah. Okay. So let's continue. So within gradient-based methods, we have basically the gradient descent algorithm where you minimize the error just by doing small steps. So that's a slow algorithm, but it's it's very efficient, and it's the basis of deep learning, for example, for neural networks. Now I'm going to talk about the other method, which is least squares algorithm. Least squares method is very fast. It's just one step. In one step, it's going to take you to the best possible output for a given problem. But it only works for linear problems. So if you have some dependence that is linear on some of the parameters, then you can use least squares method. Now, this will not work in general for neural networks, but it might work in the output layer of the neural networks, because the dependence on the last few parameters is linear. So imagine that W are basically parameters, and X is basically your input. Your linear dependence on X, on the output, on the output depending on input, is basically X times W, a vector multiplied by a matrix. Now the desired output is Y. So here we have an error function that is 1/2, and our output minus the original output, and all squared. So we want to minimize this error. Yes. To do that, we have a one-step method. So after solving the equation, the minimum of this function can be calculated immediately by showing that W is this crazy expression. This is called the normal equation. I will show you how to obtain it just here. Okay, so let me show you how to get it. So ideally, I want XW to be equal to Y. So if my output is exactly Y, then I get the error of 0. So that's the perfect approximation. No one can do better than that. So I want to get XW equal to Y. So what do we do? The first trick is to multiply by the transpose of X. Why do we multiply by the transpose of X? We could solve this as a linear system of linear equations if this was a square matrix, but this is not necessarily a square matrix. We have various input values, various number of data points is different. You're going to have different inputs here in the X value. So different dimensions. So you multiply by the transpose to make it a square matrix. After it's a square matrix, potentially you can invert it. If you invert that, you multiply by the inverse to the left. Yes, that takes away this one, and you end up with this expression over here. Yeah, I think there is a question in the chat. Let me see. Yep, correct. A square matrix. Awesome. Thank you. Yeah, so then when you have a square matrix, you can try to invert it. And let's suppose that it's invertible, then you can calculate W directly from this equation. What if it's not invertible? If it's not invertible, you can perturb this matrix to make it invertible by a small epsilon value, and it's going to be still working. The method will still work. Yes. So that's basically least squares method. It's a one-step method, but it's not always working So it doesn't work in a nonlinear dependence, only for linear dependence. Yes, let's continue. I don't know why I can't really do page down. Okay, I need to click, looks like. So here one more time we go over the gradient descent method, minimizing the weights. Yeah, this is a multi-step method. The previous one was the one-step method. If error is nonlinear function, then we can update the W weights of the system or parameters of the system by WK updated is the old parameters minus, here I should have a multiplier. I forgot to put a eta. So there should be a learning rate multiplying this function. Yeah, so with this in mind, we can see that we have basically now two methods to deal with. We have the least squares method, which is a one-step method and fast and efficient, and the gradient descent learning, which is efficient and easy to calculate. So least squares is harder to do because it doesn't work only for linear parts. Gradient descent can always be computed. Now let's look at deep learning. So how deep learning is using gradient descent method? Yes. I don't know. Yeah, most of the competitors might have completed already some machine learning courses, but if not, yeah, or you are new to the field, then let's go over what is a neural network. A neural network is basically a structure of this form where you compute the output y as dependent on the input values x1 all the way to xm. Yes, and yeah, these are inputs to a layer of neurons. And this is just one layer of a neural network. These output values these values x1, x2, xm could come from a different neurons that are in a previous layer of neurons and so forth. So you can make it a deeper neural network. This is a shallow network. It would be just one layer of neurons. These are the layers of neurons. Each connection is with a given weight. W1, W2, Wn are weights of the connection. AI x is a vector actually, and AI is a matrix, a row of a matrix. In fact, BI is basically a bias that is applied to the neural network that will influence the activation function. An activation function will be typically some kind of a smooth transition between 0 and 1 values, where 0 is an inactive neuron, 1 is an active neuron, and we have a smooth transition between them. That's fine in case of a sigmoid. Or could be another activation function is ReLU, which is maximum between 0 and x. So it's going to be 0 for a while and then x after that. I don't have now a graph for these here, but yeah, so if you imagine a function that is 0 for all the values are less than 0, and then it's just going to be the identity function. It's going to be a ReLU function that is another popular activation function. Neural network typically uses either ReLU or sigmoid, depending on what are the given goals with this problem. Okay, so let's illustrate the backpropagation algorithm. How do we learn from one layer to the other? Yes, that's basically the question here. Let's say this is a layer, let's say layer L. Let me see, how did I do? Layer L plus 1. So this here is layer L plus 1. This previous layer is layer L. Yes. Let me see. Would be good to be able to go to a node so I could scratch on this. Let me see if I could do that. Sorry, give me please 1 minute. I'm gonna
Absolutely.
change my notebook to to another one. Yes. Sorry. So yeah, I wish I would be. I realize now that I cannot draw on PDF directly. I need to drop it somewhere to be able to draw on it. And now I don't find my stuff. Yes, I found it. So let me do this again. Sorry. Okay. So can you see my notes?
Yes, we can.
Thank you. So we have here. Yeah, let me do the correction that I meant to do here. We need a coefficient, the learning rate, eta over here. That multiplies del E del WK. Okay. So for deep learning, yeah, now I can also draw the ReLU function for you guys. So ReLU function is this one here. It's 0 for a while until the origin, and here it's going to be y equal x for x greater than or equal to 0. So that's ReLU activation. It's used mostly in image processing because it's close to linear and it's very fast on the GPU. Sigmoid has kind of a graph like this, and it's basically a function of this type, 1 over 1 plus e to the minus x. It stays near 0 and near 1 on the positive infinity and negative infinity, and between them there is a smooth transition at the origin. Okay, so we want to backpropagate the error basically. So let's say that we know the error on this layer here on the outside layer, and we want to know what's the error contribution of this neuron to that particular error. So how do we do that? This is, let's say, layer L plus 1 of the network, and this is layer L of the network. Now, with that in mind, we assume that we already know del E, del. Okay, so one more thing here. I should actually draw here the output of this layer. Let's call it OK, where K belongs to layer L plus 1. So in layer L plus 1, I have this neuron. Yes. Okay. In fact, I have other neurons here as well. Yes. So there are other neurons. I'm just drawing one of them to make sure that we don't make this graph so crowded that no one will ever understand what's going on. So we have other neurons, but I don't draw them. I just want to see how this contributes to the error. So del E del OK is known. Let's say that we calculated it with backpropagation. How do we do that? Basically, the first step is easy because, for example, if this is just a plain mean square error, squared error, then you take the derivative of the error. That's going to be the gradient of the error on the output layer. Just the gradient is calculated directly from the expression on the output layer. So you can take that. It's just going to be typically it's going to be y minus output minus your output minus the desired output. So I do that for all the neurons in the output layer, and I want to backpropagate to these. This is del E del OJ, which is going to be the output, the error contribution on this particular neuron. So how can I do that here? So again, when you have the output layer, yeah, I have here the output layer. We have basically the squared error here, and the derivative of that is just O minus Y, the output what you want in the output layer minus Y. Now you suppose that we got all of these errors in the layer L+1 calculated. So once we know those, we can go back one layer, and then imagine going back from the output layer to the layer n-1. Like, let's say n is the last one, then n-2, so on and so forth, until we reach the beginning of the network. So how this happens? OK is going to be calculated as phi of zk. If we look at this picture, we can see that OK is the phi applied to zk. We assume that there is no bias here. It's OK to have bias. We can calculate with bias. Just for this illustration, I wanted to avoid that. Then I'm having zk is calculated as the sum of all outputs from previous layer. Yes. So zk connects all these layers together. Because imagine here, there are other neurons that connect here. Yes, again, I don't want to make this graph very complicated, but there are other neurons and all connecting to the zk output. Zk is then the sum of all inputs from previous output layer, from previous layers outputs Oj. So then I'm going to take the derivative of del E del Oj. It's going to be, how does error depend on Oj? It depends, error depends on OK, where OK depends on zk, zk depends on Oj through wkj. So all these create three terms in the gradient descent, in the gradient calculation for del E del Oj, which is going to be this expression. So that dependence on error to OK, which is already known. We assume that we are going backwards. Then I have the derivative, how phi depends on, so how OK depends on zk is phi of zk. So it's going to be the derivative of that dependence. And the derivative of this dependence on wkj is just going to be the wkj constant. So this is basically how deep learning is actually a gradient descent learning. And how do you update the basically the gradients here? Then, well, I should actually show you here that I can then calculate del E del wkj. I could calculate it as del E del OK times the derivative of OK with respect to zk, because that's still here, times the derivative of error with respect to wkj. When I take the derivative of zk with respect to wkj, I'm getting Oj out of it. So it's going to be times Oj, the previous output. So I can then calculate this. I forgot to explain this summation. Why do I have summation here? Because we have other neurons in the output layer, not only this one. So I have to sum up all the contributions from all of them. Okay, so once I calculated that, I can update wkj as we mentioned with the wkj minus learning rate times del E del wkj. So this is basically the 1 minute version of the deep learning. Okay, it was more like 10-minute version of the deep learning class where we would explain how deep learning works. No, I see a question. Yes, we repeat again. Yes, we repeat this from from this layer to the previous, and again to the previous, and again to the previous. And once I propagate it to the very beginning of the network, then I start again because I updated these weights. So then what I'm going to do again, propagate forward my input values to create new output. The new output still is not going to be exactly what I want. Again, I back propagate, again forward, again backward, until I get bored and stop learning stop training the network. So deep learning is typically a long process. It's going to take a long computation time. Okay, so let's continue now with fuzzy systems and how do they connect to neural networks. So you saw last time fuzzy rule-based system. Yes, the typical look how the fuzzy system look like is if antecedent, then consequence. For example, if the music is loud, then the neighbors are annoyed. Loud and annoyed are typically fuzzy systems, fuzzy sets in this setting. Yes, because we don't know what is really loud, what is not so loud. We don't have a threshold decibel value, which is loud for someone, could be less loud for someone else. So let's construct a general model for that. Typically, it would be an if x is ai and y is bi, then z is ci. For example, if velocity is low and road is clear, then acceleration, push acceleration to gain speed. For example, that would be a cruise control application, a more complicated one. Then once you have a fuzzy rule base, Mamdani fuzzy system is calculating the output of the system based on this formula, where this represents minimum operation, takes the minimum between these two values. And this represents a maximum operation, maximum for all rules. You take the maximum for all rules of the, this is the firing level of each rule, minimized with the output, corresponding output. Once you calculated the output, it's going to be a fuzzy output. Once we have that, we still want to have a classic crisp output. What do we do? For example, for your spaceship application, for the asteroid game, you still need to decide whether you shoot or not shoot. You can say you shoot 60% certainly. You have to make a cutoff. So this is done by the defacification step. The defacification step basically calculates the centroid of the output region. Takes just the horizontal coordinate of that. So here's an illustration. Let's say this is three rules actually. We have rule number 1, rule number 2, rule number 3 here. Yes, each of them has a firing level that you calculate basically on the input, on the antecedents. You calculate basically on the antecedents. Alpha 1 is actually 0 here, alpha 2, alpha 3. And the formula that we shown here is going to take you the minimum between the rule output, which is for example, the purple one here, and the firing level. And does the same for all the rules and takes a union about all of them, which is basically giving you this region. So this is the region that we get after calculating the fuzzy output. To make a single value from it, we calculate the centroid, which will be more towards this one, less towards the smaller area. So this will tell us what to do in this fuzzy system. Yes. Okay, this is Mamdani system, and it has a bottleneck problem here. This is the bottleneck problem. You have the defacification step, which is typically slow because you want to basically calculate an integral Of course, you don't calculate really an integral, but you calculate a Riemann sum that approximates these integrals, but still it's going to be slow compared to the next one, which is the Takagisogyno Kang fuzzy system. I'm not sure if you have covered this type of system in the previous talks. So Takagisogyno Kang fuzzy system has either constant output or could be a piecewise linear output. So I here took constant output for simplicity, but this could also be an AIX plus BI, a piecewise linear output. Okay, let's go with constant output. So our rule in the antecedent part is still X is AI. So if temperature is low, then heat on high. But heater on high is replaced by typical value. Let's say put the heater on 2. I don't know, maximum setting 2. Yes. So on high setting is going to be like the 2 setting, low would be 1 setting, 0 setting, do nothing, so on and so forth. So a Takagisogyno Kang system will have an output a constant value in this setting. How do you combine these? It's just going to be a simple weighted average. You make a weighted average of the output values weighted by their firing levels. These are the firing levels, and you do a weighted average with respect to those. So this is Takagisogyno Kang fuzzy system. And what's the advantage with respect to Mamdani? There is no integral here. Yes, it's directly calculated as a linear. Well, it's a yeah. Okay, I already gave out my. What is the advantage? It has a linear dependence on these W's. And if you remember, linear dependence allow us to do least squares learning. So that's the advantage of Takagisogyno systems. We can learn these parameters using least squares, just get the best value and no need for iterations in this case. All right, so how Takagisogyno system works? For every rule, it has basically assigned a W value. So for this one, let's say this is the value. For this one, it would be this one with this one. And the output is basically going to be an approximation of a given curve, yeah, let's say, on which the weights are located. Let's talk about the Anfis fuzzy. Basically, this is the first. This was the first fuzzy neural system that was implemented. Yes, and since then it has been developed and used in many applications. Actually, the system had a piecewise linear input, linear output. So let's look at this rule base. Now we have a rule base of the form: if X is AI and Y is BI, then Z is a linear combination of this form. Yes. Anfis is a Takagisogyno fuzzy system type, and we can use least squares. There is a linear dependence even on these coefficients AI, BI, CI. X and Y are input values, so those are going to be constants when you have data points that you plug in. So we can learn these by least squares. And what do we do with the other parts? How do we learn the input parts? We can set up initial fuzzy rules for the input part, and then we modify them using gradient descent. We can modify the parameters of these AI and BI fuzzy sets in the antecedent. So this is basically going with gradient descent. So how the ANFIS works, it does a step of least squares on the output, does a gradient descent on the input, and then iterates between them until the network is trained. So this is a structure of an ANFIS, and this is from the original paper by Young. And yeah, these are, for example, if you have two antecedents, then you calculate the output of these, and then you combine them in the output F as a weighted average. Yes. So it's a neural network. Recently, I have also obtained a connection between Takagisogyno fuzzy systems and neural networks in general. So any neural network, basically, let's say a one-layer network, can be described as a combination between a Takagisogyno system. I have this in the middle. This is a TS fuzzy system, and there is a ReLU activation based output here, and the linear part in the beginning this could be also replaced by ReLU according to more recent results. But anyway, so two ReLUs and the Takagisogyno system can describe any neural network. So Takagisogyno Kang fuzzy system can be seen as a neural network, and we can train it that way. Yes. Okay, what I want to also mention, that it is natural to put basically here, if these are neural networks, we would put many layers, and we would have here another layer. So this X would come from another layer of a Takagisogyno system. Yes, so here we could have another Takagisogyno system, another ReLU, and another ReLU. So we could have different layers connecting to this one, and we could make deep learning with TS fuzzy systems. Yes, in this setting. Yeah, how? Well, basically we could do the backpropagation algorithm just as well as the others, and yeah, this architecture is still. If it's a deep architecture, it's possible to do deep learning, but it's not fully investigated yet. So there is a lot of work that could go into this direction. Yes, how exactly this works, what applications you have. Anyway, so let's continue. How could we combine then? How could we build interpretable neural networks? So this is basically the method where I translate a neural network that has trained, for example, in TensorFlow, into a fuzzy system to make it interpretable. So let's start here. Using this method, this is basically the translation of a neural network into a TS fuzzy system. So a neural network can be interpreted into a TS fuzzy system of this type by direct calculation. Yes. So if we have, for example, a neural network, we train it, let's say, then we convert that into a TS fuzzy system using these formulas, right, that allow that translation. I didn't include those formulas. It's a longer algorithm. If you want details on how that is built, I can share that with you, and that in a paper in NAFIP's conference, previous NAFIP's conference, for example. So this TS fuzzy system, then I can have an expert take a look at it and interpret it. And well, we have different options here. An expert could modify it to make it add rules to it. For example, saying, oh, this is not covering the case that I want to cover. For example, I know that low precipitation in the will give us a certain phenomenon, then that rule can be explained as did. Or, for example, for the asteroid game that you are about to work on, you can, for instance, train a neural network to play the game and then translate that into a Takagisogyno fuzzy system. And the Takagisogyno fuzzy system will tell you basically what the network learned. Yes. Then we could have an expert take a look at the rules and understand, oh, this makes sense because this behavior is always matched with this output. Yes. Then the Takagisogyno system can be converted back. This is not only a one-directional conversion, this is two-directional, so you can convert it this way or that way. So this conversion allows you to train now to convert then the Takagisogyno back to a neural network and apply learning algorithms, deep learning, for example, and continue this. And basically the duality between the interpretable part and the non-interpretable learning is there. What is the problem with this? Takagisogyno fuzzy systems are only halfway interpretable. No, imagine this one here. Let's go back to this rule base. Input output are fuzzy, so those will be easy to interpret. Temperature is, for example, if you consider the most typical tipping in a restaurant problem in fuzzy, that would be basically if food quality is high and service is excellent, then tip is generous. So imagine here, this Takagisogyno rule would be if food quality is high and service is excellent, then tip is 3x plus 4y plus 15, or who knows what, some values there. Yes, so we can see that this output is not that interpretable, not as interpretable as we wish. So we want to get more interpretation to that. In that case, we can translate Mamdani systems into Takagisogyno systems and backwards. So we can make a translation between Mamdani and Takagisogyno via some direct calculations. The problem is that they are not one-to-one, so they don't translate into each other, but they approximate each other. Yes, that works out because yeah, so Takagisogyno system is an approximation of an original function. Let's say you have an original function. Yes, let's say this one is going to be the original function. You want to approximate this one. Mamdani approximates it this way, and Takagisogyno approximates it this way. Yes, if they are close enough, the Mamdani approximates the Takagisogyno as well. Yes. So this can be done by the following simple kind of translations. You have a Mamdani rule. If X is AI, then Y is BI. Based on just the parameters of the AI BI fuzzy sets, these are considered now LR fuzzy numbers, but they think about them as triangles, and triangular fuzzy numbers where xi could be xi minus 1 could be the left leg of the triangle, xi could be the vertex, and the xi plus 1 could be the right leg of the triangle. So when you have such a LR means that I could have similar things with different shape, not only triangles. So if I have those parameters, I can basically come up with a Takagisogyno approximation of it just by looking at the slope, an approximate slope that derives from the combination of AI versus BI. Change in Y over change in X is an approximate slope. And then these parameters BY can be calculated from there. So this is basically the an approach that allows you to approximate Mamdani fuzzy system by Takagisogyno system. You can also do it backwards. Why is that? Because basically here you have an approximation between them. So basically you could have TS of X minus the Mamdani system of X close enough, let's say less than epsilon. So then basically given the Mamdani, I can construct the TS. Given the TS, I can construct the Mamdani similar. Well, it's slightly different methods, but it's a straightforward method. Okay, this gives birth to a new idea where I could have a Mamdani system approximated by the Takagisogyno system. So let's start it this way. And this is, for example, in the asteroid game that you are going to be working on. You, for example, want to develop a Mamdani system for decision making. For example, turning, how much you should turn. Yes, let's say avoidance. We are looking at avoidance. You have here your ship and an asteroid is coming towards you. Yes, or more of them. Yes. The Mamdani system can be constructed to avoid these asteroids with the following type of rules. If asteroid is near and approaching, then turn away. And away means it's going to be a fuzzy set, for example. So for avoidance, you could construct a Mamdani system of this type. Then this Mamdani system is very slow to learn because, well, we know difficult to learn on something that has an integral and the COG defacification in it. So what you could do in this approach is to approximate it with a Takagisogyno system as described by this above. Then the Takagisogyno system can be translated into a neural network where you have learning algorithms that can basically train the network a little bit, then interpret it again as a Takagisogyno, then approximate, get a new Mamdani system, updated Mamdani system, which is telling you that, oh, if this is so big, I have to turn very fast. So the system will learn how to avoid danger, basically, based on data, based on different scenarios and what happens. And then your expert could analyze again, well, you are the expert in this case, you're going to be the expert understanding the game. So then you will analyze, does that make sense? If it makes sense, you continue on. Let's say that, well, usually it's going to make sense, but you realize that you didn't cover basically a case where you have another ship over here and you want to avoid going there. So then what you do, for example, then you add the rule that changes the Mamdani system. Then you need to retrain it. So go again and obtain your new explainable fuzzy system based on this approach. So this is a proposed approach. We use this in an application. We didn't use this specific approach. We did kind of. Yeah, so we use this approach in a problem from atmospheric sciences. This is about improving prediction of the El Nino southern oscillation. So El Nino and La Nina are basically climate phenomena. When it's an El Nino phenomenon, then the warming of the ocean changes the climate of the Earth. And the El Nino is typically every couple of years you have an El Nino season, and it changes the weather globally everywhere. So El Nino will make, for example, less hurricanes in the Atlantic. It's going to be also a warmer winter, and yeah, so on and so forth. Warmer, really warm temperatures in South America in the yeah, in around December, for instance. So on and so forth. So El Nino is very very important to predict. So we worked with Markel Medina on this problem. So what happens in El Nino prediction? Typical approach is to have an ensemble prediction. Ensemble means you have different statistical and dynamical models illustrated in this picture, each of them calculating its own prediction of the El Nino. And typically, then an ensemble prediction would take the average of all those. So an average of all these would be somewhat like this kind of, it's there already. I think it's there already, this big yellow one. I think it's the average. Oh no, this doesn't have the average yet. So yes, indeed, you could calculate the average of this prediction. Each of them, for example, this is a NASA's model. There is the Australian model. I don't know. There are Markov chains. There are different models. Each of them runs, and then you do. Oh, that's actually the average. Indeed. So the average is there. It's yellow. So typical idea is to use averaging for ensemble predictions. The idea that we came up with is to have more confident, so models that have higher confidence levels to get higher values in the output, basically higher skill, model skill. So we put together a Takagisogyno fuzzy system, which combines basically the above model skill with the fuzzy system, saying basically if historical error is low, then confidence in this model is low. If historical error is small, then we are more confident in that model, so it's going to get a higher weight. Then weight in the approximation is higher. So this Mandani system we translated into a Takagisogyno and then used least squares learning for the linear parts. So we can learn these coefficients using a least squares method. Yeah, you're going to get some more complicated matrices, but still linear everything. So we can calculate the least squares error from there. After that, we improved the input fuzzy sets using a gradient descent, where we use the gradient just an approximate approximation error. Yes, so we calculated this as an approximate gradient. It's a forward difference. Yes, the error after we change it minus error before divided by the change is an approximation of the forward error, the forward difference for the error. It's not very accurate, but it's giving you an estimation of the gradient without needing to really calculate this efficiently. Okay, so results for this problem. Yeah, the orange one is for example, the real data. Yes, this is the El Nino index, which is basically how much the ocean is warming with respect to this the average. And then the blue one was the ensemble prediction based on the original method, and the red one is our prediction. The green one is learning on the historical data, so we use the training, the learning algorithm for these. And then the red one is already prediction, so it stops using the data from here on, just does the prediction with the green model forward on. Yes, so in many situations it improved over the other data, but not always. As you see, this one, actually the red one is more crazy than the blue one, so the blue one was more reliable in this situation. So we have an improvement, but not consistently. Yes, so based on this model, we can obtain an improved prediction in some. That's the, but most, yeah, so on average, it produces an improvement. So if we look at data, yeah, we can see that on average, we have, this is error with the original method without the ensemble, without the fuzzy method, and these are the model errors. They are all better except the one where we have just not enough data learned yet. So if we learn enough, then you're going to have a better model in this situation using the fuzzy system. And the fuzzy system that we learned was a Takagisogyno that we trained with the data. And this is the Mamdani interpretation of it. These are the antecedents, these are the consequences. So model error, this is a signed error. So model error, low, medium, high. Yeah, so then we have different output errors. So this is how the system turned out after learning. The interesting one is these blue ones are really producing a large value, but there are very few that go into this category. So actually this blue one is very rarely used consequence. Conclusions. Gradient-based methods basically yeah, so I didn't talk about exploration versus exploitation trade-off. When you had last week or so, or 2 weeks ago, genetic fuzzy systems. Genetic fuzzy systems are exploration based methods. Exploration is basically when you explore the search space using, well, randomness or genetic algorithms or other methods. Exploitation is basically when you zoom in onto one little detail and try to make that better. So for example, exploration produces a fuzzy system and you improve it with exploitation with gradient-based method to make it better. Yes, so we can see that gradient-based methods are highly used in deep learning. So it's a good idea to basically combine them with other methods in general. So references, we have talked about these references before. Yes, Markel Medina has this paper with me, and ANFIS is by Roger Young, and so on and so forth. So that's all then for today. Thank you very much.
Thank you, Barnabas. That was fantastic. I have a quick question before
Yes.
we open up to others to ask questions. I was curious what sort of assumptions and or limitations you have on the architecture of the neural net that you are converting to a TS fuzzy system.
Yes, so the neural network, there is no limitation on, well, for now we worked with one layer only. So this is how one layer would look like. Well, sorry, I'm going to scroll back to this part. Yes. So the conversion, here we had ReLU activation. So neural network with a ReLU activation can be converted to a TS fuzzy system plus two ReLU functions, basically. One for the low pass, one for the high pass values. And between them, there is a Takagisogyno system. And it's a one-to-one. And the neural network is basically, value activation. That's the only restriction on that one. The idea is relatively simple. Neural network with ReLU activation, because ReLU has this shape, is going to be piecewise linear. If you have a piecewise linear function, the Takagisogyno with triangular membership functions is also piecewise linear. So basically the idea is to represent the set of piecewise linear functions in a different basis. And these are basically the B-spline basis, in fact. So then with one first order, and then there is a relatively easy formula to convert it. But the neural network, the Takagisogyno system would not reproduce accurately things in the towards negative infinity or positive infinity from the neural network. The neural network can have a slope for those. The Takagisogyno system would be flat, so that's changing these two are basically allowing that to be different.
I see. Thank you.
Mm-hmm. Thank
All
you.
right. I'd like to invite anybody else
Question.
if they have any questions.
I was a bit fast on these.
Oh, well, I guess we had someone ask.
Backpropagation.
Yeah.
Sure. I'm glad to. Let me go to those slides. Yeah, I went a bit fast on those. So how backpropagation works is basically here. So let's assume that we have let's start with the first step of backpropagation is basically forward step. You have an input X that goes into the network, and then you calculate every output through the network. And at the very end of the network, you get the value output. Oh, let's say. This connection basically is the feed forward step. You start with an input X and you calculate what's the output of the network on that X. Now you want Y hat to be your output, but you got to ON. So there is an error there, and you can put together the error as 1/2 ON minus Y square. Then you can calculate the derivative of error with respect to ON easily. So del E del ON is going to be just the derivative of this expression here. 2 goes to the front, goes away, and you get ON minus Y hat. So I can calculate del E del ON. So this was ON, the very last output. So I can calculate del E del ON easily. No? Now I suppose that I already calculated all of the errors up to layer L+1. So if you already calculated this one in the last layer, then this supposition allows you to go back one layer and calculate del E del O P, where P is in previous to the last layer, previous layer. So far, does it make sense? So now we suppose that we went all the way back to layer L+1. So we are already at layer L+1. We know all these del E del OK in layer L+1. So I know this one. this is another instance of that. So this is a del E del OK, another OK here where K is in layer L+1. So I know all these. How can I calculate the del E del OJ? This is what I don't know yet. So how do I calculate that? So first step, okay, let me put here on the side, I could calculate what is del E del OJ. Let me use a different color for this. So how do we calculate del E del OJ? So the chain rule, basically it's the big old chain rule from calculus, no? So you calculate, you know del E del OK. So error depends on OK. Chain rule says that I should multiply with the dependence of the inner function. OK depends on ZK, so it's going to be del OK over del ZK. Then ZK depends on OJ, so I'm going to multiply by del ZK over del OJ. And now I'm going to calculate all of them. So I know that OK is phi of ZK, then del OK del ZK is going to be the derivative of this phi prime of ZK. So that goes here. ZK, I know, is going to be the sum of all WKJ OJ terms. And now I'm taking derivative of ZK with respect to OJ. When I take the derivative of ZK with respect to OJ, then the derivative is going to return this coefficient WKJ. So therefore, del ZK over del OJ is going to be just WKJ. So once I know these, I put together a formula saying that OJ with respect to this is calculated this way. And these are, well, what I forgot here is that this is not just one neuron there, but all of them produce some dependence. So I'm going to have here an extra summation with respect to all neurons in layer L+1. So K in layer L+1. And that's what we have here. So sum up all the neurons in K layer L+1, and I get this formula. So that's how I can calculate del E del OJ. Once I know that, I can calculate del E del WKJ as well. Same process. E depends on OK. OK depends on ZK. ZK depends on WKJ. And this time the derivative of ZK with respect to WKJ is going to be OJ, because again, now you take the derivative with respect to this guy, then it returns the coefficient of that derivative. So that's basically how backpropagation updates. And then you do a gradient descent on the W's, and that's how you update the W's. And you repeat this process again and go through the very beginning of the network. Then you propagate forward the next value, then propagate backwards the error obtained there. And slowly you train the network by this back and forth with the backpropagation algorithm. Yeah. So is that making it more clear? I know it's a little complicated algorithm, but yeah. That's the main idea. Now we are very lucky that TensorFlow takes away all this headache from us and calculates the derivatives automatically. But you know, you want to understand how this works, especially if you want to implement it in fuzzy setting where there is no really a library that does that. So sklearn, for example, cannot calculate derivatives, cannot do basically this step, so you have to update the derivatives yourself. So same process would apply for fuzzy. You would have then different derivatives, different functions in there, but similar ideas probably if you want to update fuzzy. Yes. Other questions if you have?
Does anybody have any last questions for Dr. Bede? Going once, going twice? Okay. Well, thanks again, Barnabas, for giving a great talk on gradient descent, especially how it relates with neural nets and fuzzy systems. A reminder to everyone that Dr. Bede will be joining us again for another seminar next Monday on applications in reinforcement learning with fuzzy systems. So this is somewhat of a primer leading up to that. So we'll come back and talk about some very interesting applications.
Thank you very much for inviting me and bearing with me 2 times. Yeah, looking
we're happy to have
forward
you.
for next week, next week as well. See you then all next week. Thank you.
Me too. All right. Thanks,
Bye.
everybody. Bye.
Bye. Thank you.